Gravity and quantum mechanics are our most successful theories, and yet, when combined, they fall apart. They clash when both must be applied simultaneously at extremely small scales, a phenomenon that physicists refer to as the Planck regime. At this boundary, general relativity's smooth curves of space and quantum mechanics' restless uncertainty refuse to fit together. Imagine discovering that the two pillars of modern physics cannot even agree on what time means. Many of the ideas we'll explore are speculative and active areas of research, but they strike at the heart of reality itself. This video takes you into that fracture line, where physics becomes philosophy, and where the deepest assumptions about space and causality might fail you. So what happens if we try to look even closer, down to the smallest scale imaginable? Hey everyone, thanks for tuning in. Before we begin, just a quick housekeeping note. If you enjoy what I'm doing, a like and subscribe would be really helpful. It goes a long way in keeping the channel going. And don't forget to drop a comment. I'd really love to know what you think. To grasp what this smallest scale signifies, imagine gradually shrinking your view step by step. Atoms already appear vast compared to it. Molecules vanish, nuclei disappear, and even protons blur into diffuse quantum fields. Continue further, beyond the reach of current experiments, and you encounter a distance so minuscule it almost defies description, about 1.6 times 10 to the minus 35 meters, known as the Planck length. At this scale, the familiar world is expected to lose all resemblance to itself. Space, matter, and even time may acquire properties we cannot yet describe. The Planck scale is not arbitrarily chosen. It arises from combining three of nature's fundamental constants: the speed of light, the strength of gravity through Newton's constant, and Planck's reduced constant, which encodes quantum uncertainty. Together, they produce natural units of length, time, and mass. The Planck length derives from this combination, and equally important is the Planck energy. The Planck energy is roughly 10 to the power of 19 giga-electron-volts, far beyond the reach of any terrestrial collider, which explains why no accelerator technology can currently achieve it. Unlike atomic or nuclear scales, this length cannot be directly explored through experiments, making it currently beyond the reach of human tools. To understand why this is an actual boundary, consider what occurs when you attempt to observe space-time more closely. At everyday scales, surfaces appear smooth. As you zoom in sufficiently, roughness becomes evident. Continue magnifying, and the texture itself begins to seem chaotic. Many physicists envisage a similar phenomenon happening to space-time at the Planck scale. The smooth geometry of relativity giving way to a turbulent, tangled structure, often likened to foam. An illustrative image is helpful here. Imagine a calm sheet of paper that, under intense magnification, suddenly reveals tangled fibers stretching across your vision. That sudden transformation illustrates how space-time might behave at this ultimate resolution. Yet the most profound shock is that our most trusted frameworks do not apply here. Quantum mechanics predicts the behavior of particles and fields, while general relativity describes the large-scale geometry of space. Each, on its own, works exceptionally well. But when both sets of rules are used at the Planck length, their mathematics contradict themselves. The equations branch into infinities. Quantum fluctuations distort geometry so violently that the normal flow of time and the stability of curvature cannot both exist. Furthermore, the very act of measurement breaks down. At ordinary scales, you can construct a ruler or a detector and rely on its reading. At these depths, things become stranger. Dimensional arguments suggest that concentrating the energy needed to localize a particle below the Planck length would create a mini black hole. So probing smaller distances risks destroying the very object you aim to measure. Space itself resists investigation with the tools that have always defined physics. This represents a radical shift. Physics usually depends on observation. You measure something, compare the result with predictions, and refine your understanding. At the Planck scale, these rules may falter. How can you meaningfully talk about distances shorter than the Planck length when the act of questioning destroys the very structure to be measured? This is not only a technical problem, but also a conceptual one. It raises questions about whether our ideas of underlying layers of reality remain valid when pushed to such extremes. I think it's essential to add a caution, though. These limits are not derived from experimental data, but from dimensional reasoning and consistency arguments. This conclusion is based on such reasoning rather than direct evidence, so it guides research but remains open to challenge. Physicists view it as a warning signpost. If you go too far in this direction, the current equations break down, and failures like these have often signaled opportunities. The history of physics shows us that points where old frameworks collapse, such as the discovery of relativity when Newtonian mechanics failed, become gateways to deeper theories. The Planck length is another such gateway. It marks a boundary where experiment cannot lead us, but theory must leap. Theorists regard it as a horizon, visible through equations, though unreachable in practice. That visibility is enough to inspire decades of work, even if proof will be more challenging to obtain. From this boundary, researchers speculate about the formation of new structures. One possibility is that space-time itself is quantized, like matter in atoms. Instead of a continuous backdrop, geometry might consist of discrete units, appearing smooth only from afar. At its own scale, these units could shift and fluctuate, less like a calm membrane and more like a restless, stormy surface. If true, this would fundamentally alter our ideas about causality, order, and even determinism. The breakdown at the Planck scale isn't simply a failed calculation that can be patched. It shows that relativity and quantum mechanics require a union that transcends both. Just as Newton's laws were integrated into relativity as a limiting case, any eventual theory of quantum gravity must incorporate the old frameworks while surpassing them. The challenge, however, is that such a theory must also redefine the very concepts of length and time that these earlier frameworks relied upon. This makes it not only a mathematical puzzle, but also a philosophical shift in how we perceive reality. Why not wait for better technology? Because this isn't just about building bigger machines. Any effort to explore distances smaller than the Planck length requires energies so extreme that they cause space to collapse into black holes. A larger accelerator wouldn't solve this. The obstacle is inherent to the physics itself. Unlike complex engineering problems, this boundary is woven into the fabric of nature. Think of it like a dark ocean floor beneath a shallow layer where light can reach. Above, things are familiar and navigable. Below, beyond that light, lies turbulence, foam, and structures we cannot observe directly. Our only tools for that hidden zone are mathematics, theory, and imagination. Physicists continue to test their models against everything we know, hoping that one framework will prove both consistent and predictive. So at the Planck scale, space and time might transform into something no longer smooth, no longer classical. The familiar order dissolves into turbulence. And the reason, ultimately, is that the two most successful frameworks we have pull space-time in opposite directions. What works brilliantly for stars and galaxies conflicts with what works for particles and fields. When asked to coexist on the most minor scale, they collapse into conflict. That conflict is the next part of our story. Einstein's general relativity and quantum mechanics each excel within their own realms. Relativity describes the grand structure of the universe, how planets orbit stars, how galaxies influence light, how the cosmic web stretches and curves. Quantum mechanics governs the microscopic scale, where particles fluctuate in and out of existence, atoms bond together, and uncertainty prevails. Individually, both theories are robust. They form the backbone of modern science. However, when scientists attempt to unite them, discrepancies arise. Relativity portrays gravity not as a force, but as the geometry of space-time itself. Mass and energy warp this fabric, and curved trajectories then determine the motion of matter. This perspective assumes space-time is smooth, continuous, and adaptable. Quantum mechanics takes a different approach. It presumes a fixed background where fields oscillate and probabilities manifest. In this framework, particles traverse a stable grid, shifting from one location to another against an unchanging backdrop. The contrast is striking. One theory suggests the stage itself ripples and bends. The other asserts the stage remains unchanged. It's like trying to span a river with a bridge made from Lego bricks at one end and wet clay at the other. Both materials work well alone, but together they cannot create a stable structure. The real trouble appears the moment scientists try to combine gravity with quantum mechanics tools. When particles of light, matter, and other forces are described through quantum field theory, the maths behaves well. Corrections can be organized, infinities tamed, and predictions matched to experiment. However, gravity resists this effort. Every attempt to quantize gravity produces equations that spiral into endless infinities. The numbers loop back on themselves, with each correction adding more chaos instead of reducing it. Instead of gaining clarity, the calculations become meaningless. In technical terms, standard quantization of gravity is non-renormalizable. The usual method of absorbing infinities into a few measured parameters fails, and corrections create uncontrollable infinities. What begins as a calculation ends without a finite answer. This is not merely an awkward mathematical tangle. The blow-up has profound physical implications. If space-time itself is unstable in such descriptions, then events cannot be reliably linked in a sequence. That's because the clear connection between cause and effect starts to dissolve. The maths exploding is not just unsightly, it threatens fundamental concepts like cause and effect at the most minor scales. Relativity demands a transparent chain of events unfolding within a curved but ordered geometry. Quantum theory may allow randomness, but it still operates against the steady ticking of time. If, at extreme scales, space-time jitters too violently to remain coherent, the very idea of event A leading to event B becomes fragile. It's like trying to follow instructions on a map that redraws itself at random. The path itself cannot be trusted. Unlike many scientific puzzles, this conflict is not merely a technical issue. You can sharpen a telescope to improve an image or build a more powerful accelerator to push a particle further. But here, the clash runs deeper. It raises the question of whether measurements have meaning if the underlying background that supports them remains unstable. This difficulty explains why researchers often describe the task as quantum gravity's impossible puzzle. Yet, impossible here does not mean hopeless. Entire research programs, string theory, loop quantum gravity, semi-classical models, ideas of emergence, have grown from the effort. Physicists continue because such clashes in the past have heralded revolutions in knowledge. The problem is not merely about integrating one theory into another. Relativity does not fit neatly into a quantum field framework, and quantum mechanics cannot simply operate within a dynamic spacetime without contradiction. Each insists on a picture while the other denies it. That tension has driven generations of scientists to search beyond both. Non-renormalizability indicates that any attempt to introduce adjustments will be unsuccessful. More complexity in the old framework only multiplies the failure. The need is for a shift in perspective, a framework where both the geometry of space and the probabilities of quantum behavior can coexist without breaking down. Please take a moment to consider what is at stake. Relativity prompts us to view spacetime itself as an active entity. Quantum theory depends on the stage of being passive. Neither can be entirely correct in its current form, but neither can be discarded. You cannot throw away relativity without losing the structure of the universe. You cannot drop quantum theory without losing the atom. The implications extend even beyond physics. Do we view space as an objective grid that exists independently of us? Do we see time as a single, ordered arrow? Do we trust that causes always come before effects? At the encounter of these giants, each of these assumptions loses its certainty. When physicists venture into thought experiments at the Planck scale, the tidy picture of a continuous, calm spacetime begins to fall apart. Tiny fluctuations coil into distortions. Geometry itself seems uneasy. The fabric that looks steady to us from afar might, upon closer inspection, churn unpredictably. You can think of it this way. Planets tracing smooth arcs across the sky are like skaters gliding over an apparently flat sheet of ice. From a distance, the surface appears polished and smooth, but near the blade, cracks, ridges, and slush emerge. The underlying ground is no longer what it seemed to be. Seen like that, the clash between relativity and quantum mechanics is not solely about formulas breaking down. It is also about the very stage of reality taking on a new texture at its most extreme scales. That new texture hints at something stranger than either theory can explain alone. This leads us to the next chapter in the story. Physicists have proposed that beneath the appearance of smoothness lies a seething, unstable structure. A foundation that from afar looks continuous, but up close may froth, jitter, and threaten the simple flow of order we accept as usual. Here we encounter an idea that physicist John Wheeler called spacetime foam. From afar, the universe appears still and dependable. Planets orbit smoothly. Light bends in precise arcs. Space seems calm. But the proposal suggests that at the Planck scale, this impression disintegrates. The geometry of reality may churn like froth, not smooth, but frothing, unstable. Spacetime foam is shorthand for the expected quantum fluctuations of geometry if gravity is quantized, one of several hypotheses explored by theorists. Foam here is not a poetic flourish, but a way to illustrate instability. Foam does not lie flat. It is teeming with bubbles that appear and collapse. If you place your face over boiling water, you do not see a still surface. Instead, you see bursts, holes forming, swelling, and vanishing. Applying that metaphor to spacetime suggests that the very distances between points refuse to remain steady. Angles bend for a moment, then straighten, then kink again. Even the ticks of time wobble as if the clock itself were shuddering. Geometry, the steady backdrop of physics, begins to jolt. Why does this occur? Because quantum rules do not allow for stillness. Every field fluctuates. Particles, energy, even the void itself shimmer with uncertainty. When matter and radiation are stripped away, quantum rules still demand jitter. And when the field is gravity itself, the outcome is extraordinary. At ordinary scales, gravitational jitters are imperceptible. At the Planck length, they spiral into chaos. Space refuses to stay still. Shapes erode almost instantly after forming, and intervals collapse before they can be measured. According to this view, the foam teems with bubbles that for an instant resemble tiny black holes. These are not the colossal bodies that swallow stars, but microscopic apparitions. They flicker into existence, distort geometry, bend energy around them, then vanish. This process repeats endlessly, with countless tiny eruptions creating texture where smooth fabric once lay. However, it's important to note that these transient bubbles are a speculative yet widely used way to visualize Planck scale turbulence, not a settled fact. Nonetheless, as a metaphor, they illustrate how geometry might become restless and provisional. Imagine observing the ocean. From an aircraft, a calm sheet seems to stretch without flaw. From a ship, you begin to notice swells and dips. From a small boat, you feel the spray. Each point shifts beneath your feet. Space-time foam resembles that last experience. Relativity offers the craft's perspective. Smooth, continuous, stable. Quantum physics insists on the wavy nature of things up close. Both views are correct, but for different scales. The tension between them, the strain on continuity caused by turbulence, lies at the intersection. Could you think about causality? In daily life, flipping a switch causes the light to turn on. Step follows step. Relativity preserves that sequence. Geometry arranges events in a specific order, but foam disturbs this. If the geometry itself shakes, the order of events, your before and after, can become unclear. Signals lose definite paths. Two events may swap sequence depending on which fluctuation you examine. It's like trying to walk across tiles that constantly rearrange under your feet. Physics relies on order. Equations connect one state to the next. In quantum theory, probabilities evolve step by step, but these steps must be based on a reliable foundation. When foam shifts that order, the equations cannot determine which outcome flows from which initial state. The rules drift, missing the stable backdrop they need. This breakdown isn't just a technical problem. It questions the very concept of cause and effect as the foundation of reality. What does real mean if order only appears after smoothing? One radical idea is that, at the deepest level, there is no fixed sequence at all. Events may not exist as ordered facts, but rather as potential sequences, waiting for stability to emerge when viewed on a larger scale. Think of a coastline. From high above, it seems neat and continuous, but zoom in and you find fractal inlets and shifting sands. Only distance conceals the chaos. Likewise, stable causality could be nothing more than a large-scale illusion. For you and me, the key point is that this isn't just abstract mathematics. If space-time foam exists, every clock and ruler around us averages over chaos. A ticking watch seems precise because it smooths over Planck scale turmoil. Distances we measure seem exact because fluctuations cancel out over large spans. Smoothness becomes an emergent veneer, not an absolute property. Tiny traces of chaos might seep into extreme conditions, such as those found in strong gravity or stretched across the long ages of cosmic history. Nevertheless, we should be cautious. Foam remains beyond experimental reach. No accelerator can probe it. No telescope can magnify it. It is an idea, derived from combining the principles of quantum theory and relativity rather than direct observation. Alternative ideas compete. Perhaps spacetime is a network, or built from discrete units, or woven from strings vibrating in hidden dimensions. Foam is only one model, yet all these models share a message. Smooth geometry is not secure at the Planck length. Something else takes over, replacing continuity with fluctuation. This makes foam less of a problem and more of a starting point. A way to say, if gravity is quantized, this is roughly the behavior we expect. From that starting point, frameworks can develop. Some describe spacetime as a lattice of discrete patches. Others view it as a relational network where connections are more critical than distances. Still others are filaments vibrating across unseen dimensions. The terminology varies, but each owes some debt to the image of foam, the realization that at the lowest scale, geometry fluctuates. For me, the powerful aspect of Wheeler's image lies in its honesty. Foam tells you directly, spacetime cannot be the untouched canvas we once assumed it to be. Every orbit of a planet, every flash of a photon, all unfold against a background in motion. We experience the calm ocean from above, but the suggestion is that beneath, the sea churns. That leads us to the natural concern. If spacetime seethes like this, then cause and effect may not be reliable either. How can one event lead to another if the path between them reshuffles? How can you determine which moment came first when the order itself flickers? That is the deeper worry, the possibility that at the Planck scale, even causality, the most fundamental of all assumptions, might dissolve. And that is where we turn next. What if reality itself lost track of which moment comes first? In your daily world, it seems absurd. You drop a glass, then hear the shatter. You push a door, and it swings open. The order appears so obvious you barely notice it. But at the Planck scale, where spacetime itself fluctuates, that certainty may falter. Cause and effect could become unstable. Think of it like chess. On a regular board, the rules are reliable. A pawn moves forward, a knight leaps in an L shape, and strategies unfold as each move follows the last. Now imagine the board slipping apart beneath your hands. The black and white squares slide and rearrange. You move a knight, but did it land before the pawn advanced, or after? The order dissolves because the ground itself refuses to remain fixed. That is the problem faced when causal structure wavers in a quantum spacetime. Relativity insists on an iron chain of sequence. Each event has a place in geometry. Light cones map what can influence what. You might disagree on how long something lasted, but not on which event came first. Quantum mechanics treats measurement differently. It accepts indeterminacy. Apply that to geometry itself, and the clarity of before and after starts to blur. Consider a simple case. Two small masses exchange signals. Classically, one sends first, the other receives later. But if spacetime itself flickers, both histories can coexist. One version has A send first. Another has B send first. The geometry no longer selects a single truth. The ambiguity is not ignorance. It is baked into the fabric of reality at that scale. Physics stumbles here because it relies on time to frame change. Equations start with a state at some moment and evolve it forward. But what does forward mean if there is no stable clock beneath it? Physicists call this the problem of time. In canonical quantizations, the Hamiltonian constraint makes the formal quantum state appear frozen, challenging how we describe change. Without a classical background of time, even the meaning of evolution is uncertain. And yet, not every approach gives up. Some try to recover an effective notion of time by treating change relationally, comparing the ticking of one system against another. Others attempt deparametrization, selecting specific variables to serve as a substitute for time. None of these efforts is universally accepted, but they demonstrate how physicists struggle to avoid abandoning causality altogether. Still, the paradox remains sharp. If you cannot define a now, states lose their anchor, and if states have no anchor, prediction itself begins to falter. Ask yourself, if you can't define now, who or what acts as the narrator of events? Probability relies on order. You ask, given this setup, what is the chance of one outcome following another? But if you cannot pinpoint which configuration is the starting point, probability collapses into vagueness. Without cause and effect, even the concept of likelihood becomes meaningless. This is where the chessboard image haunts us again. Equations of motion are like the rules of the pieces. They only work if the board itself remains fixed. But on a shifting grid, the knight's L-shaped move may not align with the pawn's advance, and strategies disintegrate. In quantum gravity, space-time itself assumes that shifting role, causing evolution equations to lose coherence when causal order becomes uncertain. One method to capture this mathematically uses the path integral. You take an initial state and a final state, then sum over all possible geometries connecting them. But if geometry is inherently uncertain, then defining initial and final slices becomes slippery. Different slicings can be mathematically equivalent, yet describe different sequences of events. The calculation risks producing nonsense or trivial results. At its core is the idea of background independence. Classical physics typically assumes a stage on which events occur. Relativity transformed that stage into an actor. Masses and energies shape space-time itself. Mix that with quantum rules, and the stage refuses to remain still at all. There is no universally agreed background against which to measure. Observables must then be defined relationally, in terms of how objects compare to one another, not against some absolute time or point. This shift makes the basic concept of cause and effect much harder to grasp. So, what picture emerges? At scales beyond our instruments, geometry itself becomes chaotic. Instead of a precise sequence, you get intertwined webs of potential orderings. At larger scales, where fluctuations average out, causes align with effects again, and the stability we trust returns. But near the Planck length, that stability might be only temporary. The belief that everything has its cause is no longer absolute, but emergent. This matters not only for physics, but also for philosophy. Your memory depends on a chain of causes. Your planning projects are affected by causes that have not yet been observed. Suppose that the chain only holds as an approximation. In that case, your sense of order is also approximate, patched together from deeper chaos, like calm waters that, upon closer inspection, churn with foam. The question then becomes how order is restored. Without a reliable framework, stars and galaxies would never stabilize. Life would not emerge from disorder. Something must convert microscopic ambiguity into macroscopic sequence. One suggestion directly addresses the unification challenge itself. Perhaps gravity plays a decisive role. Its coupling of mass and geometry could act in conditions of deep uncertainty as a stabilizer, collapsing competing options into one realized history. That idea, if true, could make gravity not only the shaper of the cosmos, but also the foundation of reality at its most minor scale. It might not just curve space, but also determine which sequence becomes actual. Still, at this stage, this remains speculation, a hypothesis among many. What is beyond doubt is the scale of the challenge. Here, the clash of theories not only denies computable answers, but also challenges our most fundamental assumption, that time flows and that causes precede effects. If quantum gravity is ever resolved, it will do more than tame infinities. It will redefine our understanding of time itself. This naturally leads to another question. If a new principle is needed to decide when uncertainty ends, what candidate could fill that role? Could there be a force, perhaps the one already shaping galaxies, that quietly determines the timeline we experience? There is another possibility that emerges when physicists consider how uncertainty finally resolves. Gravity itself may serve as the decisive factor. This concept is sometimes referred to as gravitationally induced collapse. The suggestion is that gravity might not only bend space-time, but also determine when a quantum system ceases being a fuzzy mixture and results in a single outcome. The reasoning begins with quantum mechanics. Its rules allow an object to exist in a superposition. One particle can be in multiple locations or states at once. This effect is well demonstrated with photons, electrons, or even large molecules. However, adding real mass makes the situation more complex. Two different positions for the same mass imply two distinct curvatures of spacetime. Since gravity links mass and the shape of reality, superposition creates what appear to be two competing maps of spacetime spread across the same region. This is where Roger Penrose entered the discussion. He argued that superpositions of significantly different mass distributions generate incompatible geometries, and proposed that gravity causes an objective collapse of these superpositions. In his view, spacetime cannot accommodate the contradiction of rival shapes. The system cannot sustain two separate blueprints indefinitely. At some point, one state must prevail, and the wave function collapses into a single reality, not through human observation, but because of geometric necessity. Think of it as designing a house, with two complete floor plans in hand, both detailed. You cannot build them on the same plot without conflict. Stairs cross walls, and doors open into dead ends. They are coherent internally, but incompatible together. In the same way, each quantum state of a mass projects its own curvature, its own floor plan for spacetime. Gravity, says Penrose, refuses to allow both to exist simultaneously. Instability increases until only one can remain. The appeal of this idea lies in its ability to sidestep the puzzle of measurement. In standard quantum theory, waves collapse when a measurement occurs. But what constitutes a measurement, and why should an observer or a device interfere with the system at all? Penrose answers that collapse happens automatically. It is objective. Reality does not wait for us. Gravity itself chooses one history. Yet the simplicity of the picture conceals deep controversy. Many physicists hold a different view, that collapse is only apparent, explained by decoherence. In decoherence, a quantum system inevitably interacts with its environment, absorbing or leaking vibrations, photons, and temperature fluctuations. These interactions intertwine the system within its context. The alternatives technically remain, but they become invisible to us because the interference terms disperse. Decoherence explains why interference is suppressed by environmental entanglement, but it does not select a single outcome. Penrose-style proposals aim to make collapse objective, not just effectively hidden. Seen this way, gravity-induced collapse may not be necessary. Standard quantum rules combined with environmental noise already account for the classical world we observe. Why introduce an additional rule? However, for Penrose, decoherence alone is insufficient. It explains why alternatives are concealed but not why we experience just one reality. Superpositions could still exist, merely entangled with the environment. His proposal, therefore, insists on a deeper distinction. Reality itself demands definiteness, and gravity provides it. This idea belongs to a family of frameworks called objective collapse theories. These approaches share the belief that quantum mechanics must include a genuine physical process of collapse, not just an appearance resulting from entanglement. In Penrose's view, mass and space-time geometry serve as the trigger. Larger or denser superpositions, he argues, destabilize more rapidly. Small particles can spread widely in space and remain coherent. But as an object grows, its gravitational imprint becomes increasingly challenging to maintain in multiple states simultaneously. At some threshold, the competition between geometries causes collapse. Testing this principle is far from simple. Decoherence occurs so quickly in most systems that isolating a gravitational signature is exceptionally challenging. In the laboratory, interference has been observed with molecules hundreds of times larger than an atom. Each step upward complicates the issue. If gravitational collapse were strong, it should already prevent those demonstrations. Yet, the fact that interference remains observable at these scales rules out more aggressive versions of the theory, leaving only moderate or subtle collapse rates as possibilities. Astrophysical probes may offer alternatives. Neutrinos traveling across cosmological distances pass almost undisturbed through space. They provide a venue where environmental decoherence is minimized. In principle, their flavor oscillations could reveal whether gravitational collapse has quietly erased superpositions during transit. If irregular patterns emerged in those oscillations, it might signal that gravity is intervening. However, the results remain inconclusive so far. This remains a subject of debate. Experiments to differentiate gravitational collapse from decoherence are exceedingly complex and currently inconclusive. If Penrose is correct, the implications would be enormous. It would mean gravity is not merely a passive framework for motion, but an active judge, pruning the possibilities of the quantum world. Collapse would occur naturally, without the need for observers or measurements. Every apple falling, every planet orbiting, every measured quantum system would embody the same principle. When the tension between geometries becomes unsustainable, gravity itself determines the outcome. But if collapse is real, the consequences extend far wider. It would unify the smallest with the largest, transforming the same force that curves galaxies into the agent that produces definite outcomes for particles. The measurement problem, one of the deepest puzzles in quantum foundations, would then be reframed. Instead of consciousness or observation, it would be curvature that ends uncertainty. Yet even this must be approached with caution. The proposal is bold, but evidence is lacking, and debate continues. For me, what makes this compelling is the role it assigns to gravity as more than just background geometry. It becomes the arbiter, the principle that turns possibility into fact. This vision places the quantum and the cosmic on the same footing. Still, others would remind us that quantum mechanics remains consistent and effective without this addition. Objective collapse is far from universally accepted, and without decisive experimental confirmation, it remains one of many candidates. You might then wonder, how could we ever test whether gravity collapses wave functions? That question drives ongoing efforts, from tabletop interference experiments with larger and larger systems to ambitious astrophysical observations. The results are still out of reach, but the pursuit itself clarifies what is at stake. This leaves another possibility open. perhaps gravity never collapses anything at all. Maybe it is not quantum in the usual sense, but something entirely different. Instead of quantizing gravity alongside all other forces, perhaps it belongs in a separate category. That alternative raises its own puzzles and opens new avenues for understanding how quantum matter and curved space-time might coexist. What if gravity does not need to be quantum at all, but could remain a classical field guiding the quantum world? Initially, this seems contrary to everything physics has taught us. All other forces, electromagnetism, the strong and weak nuclear forces, have shown clear evidence of quantization, with fields mediated by particles. Gravity, however, might be different. Some hybrid approaches propose that matter retains its quantum nature, while the stage it moves on, space-time, remains classical. This concept is known as semi-classical gravity. The formulation is simple. Quantum fields evolve according to their usual probabilistic rules, but they do so within a space-time described by Einstein's equations. Instead of trying to quantize space-time itself, you allow geometry to stay smooth. The coupling works through a straightforward prescription familiar within the field. The standard semi-classical ansatz replaces the Einstein source with the expectation value of the quantum stress energy tensor. On the left-hand side of Einstein's equations, space-time curvature remains classical. On the right, quantum matter influences it through its averaged energy and momentum. This approach permits quantum uncertainty to influence geometry without requiring gravity itself to become quantized. You might wonder whether such a hybrid can be consistent. Critics argue it cannot. They cite classic thought experiments, Epley and Hanna in the 1970s, and Page and Geilker later, that suggest these models could allow violations of the Heisenberg uncertainty principle, or even fail to conserve energy properly. The argument is that by measuring the gravitational field of a quantum state, one could access forbidden information about its position or momentum, undermining quantum limits. Or, if quantum states jump abruptly, then space-time curvature would have to change instantaneously, creating or destroying energy in ways relativity forbids. These are serious accusations. If uncertainty is broken, quantum mechanics loses its foundation. If conservation laws are violated, relativity breaks down. That is why many physicists assume gravity must itself be quantized. However, these concerns are not universally accepted. Counter-arguments suggest that some of the original thought experiments rely on impossible measuring devices, which would themselves violate physical law. Others demonstrate that carefully constructed hybrid models do not necessarily enable faster-than-light signaling or breaches of relativity. In other words, the debate remains unresolved, and criticisms may not apply to every possible semi-classical framework. To understand why semi-classical gravity is appealing, consider what it avoids. Traditionally, quantizing gravity leads to mathematical infinities that cannot be renormalized. Every attempt to adjust the calculation results in more uncontrollable results. By maintaining a classical approach to gravity, these issues are sidestepped, thereby preserving the elegance of general relativity. At the same time, quantum fields in curved spacetimes can still be calculated. This is how predictions of Hawking radiation from black holes or particle creation in expanding universes are derived. These calculations have physical credibility, even if the underlying geometry remains classical. Such successes prompt researchers to ask, do we truly have to quantize space-time? One way to visualize this is through a simple analogy. Imagine combining a digital clock with a smooth mechanical gear. One part ticks in steps, while the other turns smoothly. Initially, they seem incompatible, but with the proper connection, The digital pulses can drive the gear's smooth motion, and the gear's rotation can regulate the ticking. Critics worry that such gearing will always be unstable in the long term. Supporters argue that if designed carefully enough, there is no fundamental contradiction. The two can coexist, even if they operate under different rules. Another question is whether quantization itself is a natural law or merely a pattern we've overgeneralized. Every other interaction we study shows discrete quanta, so we expected gravity to follow suit. But perhaps that expectation is flawed. Maybe gravity operates by different rules. Not broken, just different. If so, unification may need to shift from insisting that everything share a single framework to accepting that different forces adhere to their own principles. It wouldn't be the first time physics has had to abandon neat symmetry in favor of what evidence indicates. None of this is confirmed by experiments yet. We cannot place a graviton detector in a lab, nor can we directly investigate individual quantum systems solely through their gravitational effects. Demonstrations of quantum behavior have grown to include large molecules and tiny mechanical devices, but the gravitational influence of such systems remains minimal and beyond current measurement capabilities. For now, no experiment rules out semi-classical gravity, nor does any conclusively support it. That uncertainty keeps the possibility open. Some researchers even propose moving beyond direct arguments and suggest that a different conceptual language could be necessary. Instead of debating whether space-time is quantized or classical, perhaps the solution lies in rephrasing theories in terms of information, the rules for how systems record and transform states. Such approaches imply that the clash between classical and quantum might only appear fatal because we continue to try to resolve it within too narrow a framework. Change the perspective, and hybrid models may no longer seem inconsistent at all. For me, what stands out in semi-classical gravity is the pause it demands. Physics seeks unity, but perhaps unity doesn't mean treating all forces the same. Here, space-time could remain classical, while matter is quantum, a divided but workable compromise. It suggests that the so-called impossible puzzle of gravity's quantization might not be necessary after all. Gravity could guide the cosmos without itself becoming quantized. At the same time, the unresolved problems are severe. How does a smooth classical field keep pace with sudden quantum jumps? Can violations of uncertainty and conservation be wholly ruled out in every scenario? No one has definitive answers yet. Until these challenges are addressed, the possibility remains uncertain but active. Semi-classical gravity remains a plausible option, but it must address these fundamental consistency issues. And confronting those issues naturally leads to another idea. Perhaps it is not only gravity's quantization that should be questioned. Maybe the very fabric of space-time itself is not fundamental, but something that emerges from more basic processes. Could the stage of reality you experience daily be less fundamental than it seems? Temperature provides a helpful hint. No single atom contains heat as you perceive it. Heat is collective behavior, the buzz of many atoms colliding. You treat it as real, but it only emerges at scale. Emergent spacetime takes this lesson seriously. It implies that the space and time you navigate are not the foundation, but higher-level patterns arising from deeper processes. This concept is known as emergent spacetime. Instead of imagining reality as a blank canvas that matter occupies, emergent models see the canvas itself as a secondary product. One analogy explains this quickly: the surface of a lake. You see waves, gentle ripples, calm stretches. Yet these surfaces exist only because of interactions beneath, where countless molecules push and pull against each other. The surface is real, but it depends on deeper motions. Emergent gravity applies this idea to the universe itself. Distances, directions, and the flow of time may all be second-order effects. For centuries, physics assumed the opposite. Newton proposed absolute space and time. Einstein refined this view with relativity, allowing space-time to curve, stretch, and bend. But even then, the stage itself was taken for granted. Emergence challenges this assumption. It rewrites space and time not as primitives, but as outcomes, similar to how pressure or sound emerge from many atoms, even though no single atom carries them individually. Consider sound waves in air. Each molecule vibrates randomly. None contains frequency or pitch. But when billions move together, waves form. They carry music, though no single particle produces it. The emergence of space-time suggests that geometry is also like this. No single element deep below is space, but their collective pattern creates what you measure as geometry. Seen this way, the challenge of quantizing gravity becomes clearer. If space-time is emergent, asking to find a graviton might be misplaced. It would be like demanding to see a particle of heat before atoms were understood. The thing you are quantizing may never have existed at the deepest level. What matters is the hidden microstructure from which curvature arises. Information theory supports the idea. Quantum systems are connected in entangled networks at their core. Their states cannot be separate. Correlations bind them together. Some researchers suggest that geometry itself is just these correlation patterns scaled up. In this view, distance isn't an external measurement, but arises from the level of entanglement. The stronger the entanglement between two subsystems, the more close they seem. Patterns of correlation outline the shape of geometry like pixels forming an image. And what about time? To you, time seems like a continuous flow, second after second. But if time is also emergent, then there's no universal clock in the background. A moment would be entirely defined by the relationships between components within the system. Order and duration might arise from correlations, rather than an external cosmic clock. What you see as past and future might only appear when enough patterns stabilize together. String theory, especially in its holographic form, provides strong supporting evidence. In some dualities, a gravitational spacetime theory within a volume is precisely equivalent to a non-gravitational theory on its boundary. This is called holographic duality. It implies that everything you think of as spacetime inside can be reconstructed from more fundamental data on the boundary. Neither description is more basic. Both are translations of the same underlying structure. Practically, this means that spacetime, as we perceive it, emerges, similar to a hologram, from more straightforward informational rules. This realization challenges assumptions about dimensions themselves. If spacetime is emergent, the number of dimensions might not be fixed. At familiar scales, there are 3 spatial and 1 temporal dimension. In different energy regimes, other dimensional structures could be more natural. The number of dimensions of reality may not be absolute facts, but rather adaptable properties. Emergent approaches do more than reshape philosophical questions. They change the core issues in physics. The apparent conflict between relativity's smooth geometry and quantum mechanics' restless fluctuations becomes less sharp if both are just compelling descriptions. Gravity would no longer need to be quantized directly. Instead, quantum rules would apply to the underlying constituents, with spacetime geometry emerging as a secondary effect. The conflict eases because the assumption creating it is abandoned. This reframes even everyday experience. When you walk across a room, glance at a clock, or trace the orbit of a planet, you are moving within a large-scale approximation. What feels stable and continuous may be stitched from hidden connections. Space and time, so familiar that you rarely question them, could be statistics drawn from more primitive elements, just as temperature is derived from atomic jostling. Black holes make this concept testable. Their entropy, the count of hidden states consistent with the horizon, directly indicates the microstructure. The vast number of possible states packed into a horizon suggests that space-time itself may conceal a detailed foundation. The surface area that encodes their entropy isn't just a curiosity, but a hint that space-time has components after all. Emergence thus provides a framework for interpreting horizons not as paradoxes, but as proof of richness. This aligns with ideas you've encountered before. Foam-like behavior at the Planck scale might not signify a breakdown, but rather a glimpse of the deeper relational web that encodes space-time. Instead of failure, it becomes the visible trace of emergence forming. The challenge becomes, can we look beyond the foam to read the hidden code underneath? Philosophy also intersects with physics here. Thinkers have long debated whether space and time exist as separate frameworks or only as relations. Emergent models strongly support relational views, now backed by a solid theoretical foundation. A place and a moment may not be primitive facts, but summaries of how constituents connect. The continuous backdrop of space-time dissolves into structures of correlation, networks that generate the illusion of smoothness. And this offers a solution to the persistent puzzle of quantizing gravity. Perhaps no graviton has been discovered because it may never have existed. Just like temperature, there's nothing fundamental at that level to quantize. Gravity as curvature is a description at scale, not an essential field. The granularity is elsewhere, in qubits, in entanglement, in holographic codes. Attempting to quantize space-time itself might be like trying to quantize temperature, the wrong thing at the wrong level. That conclusion is unsettling. It implies that what you perceive as reality, the stability of distance, the structure of time, is temporary. Space as a statistical concept, time as a rhythm, motion as a pattern through correlations. It represents the ultimate reversal. The stage itself might be secondary to actors you cannot see. This possibility opens a new frontier. If space-time is emergent, how can you confirm it? What kind of phenomenon could uncover such hidden structure? Surely such a signal would require extreme conditions, where traditional geometry starts to strain. Some corner of nature where entropy, information, and space-time all converge, to hint that a deeper layer exists. And in fact, there is a natural candidate already present in the universe, a place where gravity, quantum principles, and thermodynamics meet under the most extreme conditions known. A place where physics itself seems to tear apart. Black holes may be remote and challenging to observe, but they serve as the clearest natural clues to the study of quantum gravity. These objects push theory into realms no laboratory can reach. They compress matter so intensely that gravity, quantum mechanics, and thermodynamics are forced into the same framework. If you want to understand how the universe behaves at its extremes, black holes are an essential case study. The breakthrough came with Stephen Hawking's insight in the 1970s. He demonstrated that black holes are not completely silent, but should emit radiation through quantum effects near the horizon. Virtual particles briefly appear, and in the extreme geometry of a black hole, one partner can fall inward while the other escapes. Hawking derived this from quantum fields on a curved background, an elegant, semi-classical argument, but it remains unobserved directly. The signal is too faint for any telescope to detect. Nevertheless, the prediction is significant because it links three major branches of physics: quantum mechanics, gravity, and thermodynamics. If black holes radiate, then they have a temperature. And temperature implies entropy, which counts the microscopic configurations a system can have. For a gas, those are molecules moving about. For solids, they are atoms vibrating in place. But for a black hole, ordinary matter has vanished into singular collapse. What are its microstates? The idea that black holes possess entropy raises a crucial question. What microscopic atoms of spacetime exist that can be counted as their degrees of freedom? The Bekenstein-Hawking formula provided the initial answer. Entropy is proportional to the surface area of the event horizon, not the mass, not the enclosed volume, but the location of the boundary itself. Imagine graph paper where each square holds one bit of information. The event horizon resembles graph paper wrapping a sphere. The larger its surface, the more data it encodes. The conceptual leap is profound. Data is stored not within the volume, but across the horizon itself. This is why people often describe black holes as holographic. This connection between entropy and area transformed the field. It implied that geometry might be quantized, constructed from discrete patches. Each square of Planck area on the surface acts as a fundamental unit of spacetime. Many approaches to quantum gravity have tested themselves against this challenge. If you cannot reproduce the Bekenstein-Hawking relation, your theory is fragile. If you can, it passes the most basic test. String theory addressed that challenge for specific classes of black holes. In this context, quantum states are vibrations of strings. For certain near-extremal black holes, the count of string states matches the Bekenstein-Hawking entropy, exactly proportional to the horizon area. The achievement here is that the same framework already includes a mode similar to the graviton. Strings, vibrations, and spacetime geometry are unified in one description. Loop quantum gravity approached the problem from a different perspective. Instead of extended strings, it quantizes geometry itself. In this model, quantum lines form a network called a spin network. Where those lines puncture the surface of a black hole horizon, they generate tiny units of area. Counting the various ways the spin network can intersect, the horizon reproduces the entropy law. Although the fundamental structures differ, the result remains the same. Entropy scales with area. Causal set theory, which considers spacetime as a discrete set of events ordered by causality, also achieves this relation. That convergence is remarkable. Three vastly different models, vibrating strings, quantized geometry, and discrete causal networks, all mimic the same entropy pattern. This is why black holes serve as benchmarks for quantum gravity. Any credible theory must satisfy its criteria. The Bekenstein-Hawking relation therefore acts as a significant constraint, neither optional nor trivial. These findings have bolstered the idea that space-time is composed of microscopic components. If you can count these, you can explain entropy. Nonetheless, the finer details are still uncertain. String theory's clear matches generally occur in higher dimensions or under particular conditions. Loop quantum gravity introduces correction factors that depend on the choices made within its framework. Causal set theory is still in development, with its dynamics being continually explored. No approach currently provides a complete, comprehensive description applicable to all black holes as observed in nature. The issue is further complicated because Hawking radiation itself remains unobserved. The temperature of astrophysical black holes is so low that the cosmic microwave background obliterates it. Even a stellar mass black hole would radiate at a temperature far lower than that of the universe. This makes direct detection impossible with existing instruments. Some researchers turn to analog systems, such as artificial horizons in fluids or optical setups, that mimic the equations of black hole radiation under laboratory conditions. In these limited systems, Hawking-like radiation has been proposed, but the evidence is inconclusive. All of this suggests that black hole entropy is one of the most profound theoretical insights we have, rather than an empirical fact. Nevertheless, the clue is compelling. No other system captures the interaction of spacetime geometry, quantum mechanics, and thermodynamics in this way. Each black hole, if Hawking's reasoning is correct, conceals the fingerprint of microscopic physics beneath its horizon. That fingerprint demands that spacetime itself must have a granular structure. To illustrate this in everyday terms, consider an ordinary thermodynamic object, such as a kettle boiling water. The steam's temperature and entropy are large-scale properties, but you know they originate from countless molecules bouncing around. When you deduce the microscopic rules from this large-scale behavior, you arrive at atomic theory. Likewise, the temperature and entropy of black holes function as large-scale properties that suggest the existence of hidden space-time molecules we have yet to identify. For this reason, black holes are not just astrophysical curiosities. They serve as the testing grounds for new physics. They require that a quantum theory of gravity explain why entropy scales with the horizon area, why radiation emerges at all, and how microstates combine to form macroscopic curvature. If these conditions are not met, the theory collapses under its own weight. If they are met, the journey toward unifying fundamental physics becomes more apparent. Black holes also advance other debates. If space-time is emergent, horizons could be the most visible sign of its fundamental code, boundaries that show how information is stored. If gravity results from the collapse of quantum states, evaporation could be the key to understanding when and where these collapses happen. If gravity is purely classical, black holes present new puzzles about how classical geometry can engulf quantum matter. Each view ultimately centers on the event horizon, so black holes provide constraints, but they do not yet determine which framework is correct. They are like tests set by the universe that all theories must pass. Yet, the examiner has not fully revealed the marking scheme. The simple relationship between entropy and area does not tell us whether space-time is emergent, whether gravity is quantized, or whether collapse is objective. It only establishes a non-negotiable standard that theories must meet. For now, theory advances where experiment cannot. Nevertheless, the desire for data remains strong. Researchers continue to seek indirect evidence through analog horizons, gravitational wave patterns, or perhaps the behavior of quantum systems affected by gravity in the lab. None are conclusive yet, but all highlight the importance of testing these ideas whenever gaps become apparent. This is why black holes continue to hold such significance. They remind us that extremes are not only destructive, but also instructive. By existing, they impose demands on theory, and by resisting straightforward answers, they keep us searching. Black holes give us the theoretical constraints we need. However, the next challenge is clear. Can experiments conducted here on Earth also contribute? That question brings us to the edge of what is possible today. Experiments at the frontier of measurement are now being designed to explore whether gravity itself is a quantum phenomenon. The most straightforward method under serious consideration is called QGEM, quantum gravity-induced entanglement of masses. Although simple to state, the idea is challenging to implement. Prepare two masses in spatial superposition, isolate all influences except gravity, and observe whether entanglement emerges. That would constitute a clear sign of quantum gravity. Entanglement is the core concept. In quantum mechanics, two systems can become linked such that their states are inseparable. Manipulate one, and the other instantly reflects that change, regardless of the distance between them. Photons and electrons have been entangled many times in laboratories. If gravity alone can entangle two masses, then gravity must be a quantum phenomenon itself. A classical field cannot generate entanglement. The experiment is designed as follows. Place two mesoscopic objects, such as nanospheres, close enough for gravity to be significant, but shielded from all other influences. Could you prepare each mass in a delicate superposition of two possible positions? If gravity is only classical, the two masses will remain uncorrelated. If gravity is quantum, they will exchange information and become entangled. The outcome would be observable in interference patterns that cannot be explained by classical physics. Until recently, this seemed impossible. Masses large enough to produce measurable gravity decohere nearly instantly. Vibrations, photons, or even the slightest thermal disturbances quickly destroy superpositions. However, advances in optomechanics, where laser light manipulates tiny mechanical objects, are pushing the boundaries of what is possible. Suspended nanospheres, cooled and levitated in high vacuum, are approaching conditions where such an experiment might become feasible. For the first time, controlling objects heavy enough to generate measurable gravitational attraction while still treating them quantum mechanically may be within reach. The challenges are significant. Decoherence constantly threatens to eliminate quantum behavior. Even if thermal noise is eliminated, Casimir forces, quantum forces between nearby surfaces, could distort results. Background seismic vibrations, air molecules, or stray electromagnetic fields can drown out the tiny effect. In fact, the gravitational attraction between the test masses is so faint that even minute environmental fluctuations can overpower it. Designing an apparatus where gravity is the only relevant effect is the primary difficulty. Setups inspired by the classic Cavendish torsion balance offer guidance. In the past, physicists measured the gravitational attraction between lead spheres by detecting tiny twists on a suspended rod. In modern proposals, the role of lead spheres is played by small, suspended nanospheres or resonators, cooled nearly to absolute zero. Isolation chambers keep them floating in a vacuum, while lasers both prepare and read their quantum states. The sensing aim is subtle. If the two suspended objects influence one another only through gravity and end up entangled, it would confirm the quantum nature of gravity. If entanglement is observed, it would provide strong support for a quantum description of gravity. No classical framework can replicate the phenomenon of quantum entanglement. However, researchers emphasize caution in interpreting any null result. A failure to observe entanglement may not mean gravity is classical. It might simply be that decoherence, environmental noise, or hidden loopholes masked the effect. That is why these experiments require extraordinary care and design. There is momentum in other directions too. Optomechanical devices, oscillators coupled to mirrors or resonators, are being refined to detect the gravitational influence of nearby particles at quantum levels. In these designs, The slightest correlation between oscillators could indicate that space-time itself exhibits quantum fluctuations. The limiting factor is sensitivity. The instruments must suppress even quantum noise within the detectors themselves. This means researchers need to prepare the experiment in quantum states and also design measurement tools that behave quantum mechanically. Another approach builds directly on tabletop Cavendish experiments. Instead of measuring entanglement, some proposals aim to detect the direct gravitational effect of quantum superpositions. For example, a mass placed in a superposition might exert different forces on a test oscillator depending on its position. Measuring that tiny displacement could reveal whether gravity responds to the average position of the superposition, as in semi-classical models, or to each branch individually, as a quantum field would predict. It is a more modest approach, but it carries the same stakes. What makes these efforts so remarkable is their scale. Unlike large colliders or cosmic telescopes, these tests can be conducted in small laboratories. Cryostats, lasers, and vacuum chambers replace particle accelerators and black hole horizons. That alone indicates a turning point. The quest for evidence about quantum gravity is being fought not only at the edges of the universe, but also on quiet tables in university basements. The stakes remain high. Observing gravitationally mediated entanglement would be one of the strongest indications that gravity is quantized. It would support decades of theorizing in string theory, loop quantum gravity, and related frameworks. Conversely, if such an experiment closes all loopholes yet fails to detect entanglement, semi-classical or emergent alternatives gain credibility. Either way, the assumption that space-time shares the exact quantum nature as other fields would no longer be mere speculation. It would be grounded in data. For me, this possibility feels astonishing. After nearly a century of theoretical arguments, the measurement might come down to an apparatus small enough to fit through a door. A quiet tabletop experiment, 2 suspended spheres, lasers, and silence could settle the question of quantum spacetime. The contrast is striking. Perhaps the most significant question in physics could be answered by one of its smallest instruments. As evidence emerges, one thing is sure. Either outcome will transform our understanding of gravity, evidence for quantization, or genuine support for emergent or semi-classical alternatives. And that naturally raises a deeper question. If the very fabric of spacetime can be challenged in this way, what does that imply for how we perceive reality itself? Rethinking reality starts with a provocative idea. Space and time might not be fundamental after all. Instead, they could be large-scale effects that emerge from deeper structures we have yet to uncover. If this is true, then your most basic intuition, that the universe unfolds against an independent backdrop, must shift. Physics here overlaps with philosophy, because the question is no longer about solving equations, but about what you actually mean when you say something exists. Two of the clearest consequences can be stated directly. First is the problem of time. In canonical quantum gravity, the standard Hamiltonian equations seem to eliminate time as a parameter. Everything appears frozen. For us, that creates a contradiction. You remember yesterday. You plan for tomorrow. Yet in theory, time does not pass. Physicists refer to this as the problem of time. It is technical, but the implications are personal. If the universe lacks a master clock, then change may only seem relative to other processes, not as an absolute flow. Second is background independence. General relativity already demonstrated that spacetime cannot be fixed. It must respond dynamically to mass and energy. Quantum gravity takes this further by requiring a description that makes no assumptions about any geometry beforehand. But definitions vary. Some string theorists see background independence in holographic dualities. Researchers in loop quantum gravity emphasize that their models are explicitly background-free. Both groups see advantages, yet no consensus has been reached on the term. This debate raises a deeper question. How can you describe reality consistently when the stage you usually rely on, the fabric of space-time itself, may not exist at a fundamental level? Together, these two consequences challenge familiar categories. If there is no reliable time parameter, then even before and after lose certainty. If there is no fixed background, then even the concept of location becomes unstable. You can imagine living on shifting ground, where maps redraw themselves as soon as they are made. What you considered secure becomes conditional. For philosophy, the significance is profound. In everyday life, time synchronizes with clocks and calendars. In physics, it organizes change in equations. But if the mathematics that governs the universe completely omits it, then what is the status of your lived sense of passage? Perhaps time is emergent, an illusion that arises at large scales, or possibly new interpretations allow you to retain it in a revised form. Either way, ontology, your understanding of what exists, must face revision. Ontology begins with categories. What qualifies as an object? What qualifies as a field? In ordinary physics, you answer by pointing to positions in space and times on a clock. But quantum gravity erodes both points of reference. Space-time itself, when quantized, produces fluctuations that make the very idea of here and now unstable. If those lose meaning, then fields that assign properties to those points cannot be fundamental. You are left with relational definitions only. Objects exist not by occupying space, but by how they connect. Consider discreteness. Classical space-time appears smooth and continuous. You rotate, shift, and translate without breaking it. Symmetries depend on that continuity. But if space-time is discrete at the Planck scale, made from indivisible units, the challenge is clear. How do smooth laws emerge from granular foundations? The analogy is liquid water. To you, it flows without gaps, but at scale, it is molecules bouncing. Something similar might produce continuous geometry from discrete grains. Still, that is an assumption, and one that must be tested. Step back, and the theme becomes clear. Categories destabilize at the foundations. Time might be absent. Backgrounds may not exist. Fields may fail where points are fuzzy. Continuity itself may be an illusion. These are not speculative flourishes, but unavoidable questions, prompted by the mathematics of quantum gravity. The simple reason is that infinities, causal ambiguities, and failures of unification demand new concepts. What collapses in equations is mirrored by a collapse in philosophy's basic terms. The effect is akin to discovering that the Earth has a molten interior. People once thought the crust extended downward, solid and steady. Finding a fluid core changed the planet from unshakable stone to dynamic, restless matter. The same happens here. Below the apparent solidity of space and time lies a turbulent base, not firm, but provisional, not absolute, but emergent. This perspective does not eliminate causality, but makes it conditional. In relativity, cause follows effect within rigid cones. In quantum spacetime, order may vary. One path may depict signal A first, another signal B. Without an agreed-upon geometry, universal time may break down. And if quantization is imposed, some models go even further. In specific canonical approaches, Equations omit time altogether. Physical states appear frozen. For physics, this poses a technical challenge. For you, it highlights the difference between remembering yesterday and expecting tomorrow. You don't need formal maths to grasp the philosophical significance. Consider everyday life. You perceive time as a sequence which underpins your decisions and actions. Remove that sequence, and the connection between memory, expectation, and present action weakens. For philosophers, this challenges the very notion of ontology. What role does change play if the universe does not encode time at its core? Is your experience an illusion, or does it suggest that our current theories are incomplete? Both possibilities remain alive. Causality, ontology, background, and discreteness. Quantum gravity compels philosophy to revisit age-old debates with renewed urgency. These are not mere armchair speculations, but necessary reconstructions. A universe without universal time cannot be understood through traditional means. A universe with a dynamic background implies that points and locations are not absolute. A discrete foundation for a continuous world makes emergence central, not marginal. Does this seem unsettling? It should, yet it is also productive. Without such puzzles, physics and philosophy risk stagnating in their own assumptions. With them, new paths open. Problems like a lack of time are not obstacles, but catalysts that drive refinement. Theory leads philosophy to rethink categories. Philosophy sharpens the concepts physicists need in their quest for meaningful equations. Each field stimulates the other, generating progress neither could achieve alone. For you, this is the transformation. You realize that categories you trust, time passing, space stretching, causes leading to effects, might be approximations. That realization itself is valuable. It loosens rigid images and creates space for flexibility. You see how ideas once considered permanent can break down and reform. And you glimpse a universe that may be less fixed, but more open to exploration. Even if no final answer arrives soon, this shift is worthwhile. These questions not only erode certainty, they expand your way of thinking about the cosmos. They challenge you, but also offer a calm invitation to broaden your perspective. Without clarity on space-time, on time, or on causality, unification remains elusive. But those uncertainties reveal just how deep the puzzle runs, and that is quietly exhilarating. So the inquiry continues. Rethinking reality does not end in despair, but in renewed interest. You are not merely patching theories. You are revising the map of existence itself. What matters is not only whether quantum gravity is solved, but how its questions reshape your understanding of what the universe is. And once that understanding shifts, a broader insight begins to emerge, one that changes how you perceive the experience of reality from day to day. Quantum gravity points to a profound truth. Space and time may not be the solid foundations you assume, but emergent features of deeper structures. Relativity's smooth curvature, joined with quantum uncertainty, suggests the stage itself could be constructed, not given. If space-time is emergent, then nothing in reality is beyond questioning. What you treat as bedrock may be provisional, like temperature or sound, fundamental in use, yet derivative in nature. Quantum gravity prompts us to question our most basic categories: space, time, and causality. And even without final answers, the attempt deepens our understanding of reality.